Good afternoon, good morning, depending on where you're joining us from today. This is Mike Mazzarese. I'm a senior engineer with AST Environmental, based in Denver, Colorado. And welcome to our last webinar of the calendar year. So thank you to those of you that have attended these over the course of the year. If this is your first one, welcome. And if you are interested in our previous webinars that we've given over the course of the year, or I guess last few years, you can go to our website, astenv.com, and we have all those webinars archived. And of course, if there's something specific you're looking for, please feel free to reach out to me after we wrap up here today. So the focus of today's webinar, as you can see from the title, is we're going to be focusing on the injection of slurries, specifically in applications where we get direct push technology or DPT refusal. Okay. So briefly, just review what we consider the RPI group, or what we call the RPI group. So RPI, the founders of the group, they're the top of this three-legged stool. They are the developer of the technologies that we'll be talking about today, the activated carbon-based technologies. They also operate what we call our project support laboratory, which is based in Denver. That's their website there. And AST down there on the left. So that's my company, and we're tasked. Our role in the group is to provide project assessment and design for projects within the US and as well as internationally, and also provide QA/QC on the field implementation work. And there's our website that I've already mentioned before, astenv.com. And there's just some bullets on the services that AST provides. We're an in-situ remediation contractor, and most of our work revolves around the injection and design, excuse me, of the trap and treat technologies that we'll talk about briefly today. But we do get involved with other technologies as well. And we also have an environmental construction group as well. And the third leg of the stool is our authorized installer network that you see down there on the right. And those are AST generally operates in the eastern part of the United States, and within that footprint, as well as outside, we've got other companies that we've partnered with to be able to have the proper equipment and training and personnel on site to make sure that that these projects are implemented properly from the field standpoint. So this is where we have presence within RPI group within the United States. Canada, Scandinavia, and Not Pictured is our partner company that is based in Australia, which is NUMAC. So we're not going to delve too much into the individual technologies today. We're really going to focus on really just the slurry applications, but we are going to refer to these, especially when we get to the back end project summaries. So if you're not familiar with these, we'll just go through them really quickly. The top two, BOSS 100 and CAT 100. BOSS 100 and CAT 100 are specifically for chlorinated solvent remediation. BOSS 100 is an abiotic technology, similar chemistry to zero-valent iron. And the CAT 100 is a modified version where we add an electron donor and some bacteria. BOSS 200 is primarily for treating petroleum hydrocarbons. That consists of, besides activated carbon, thermal electron acceptors, so sulfate, nitrate, nutrients, as well as bacteria. And BOSS 200 Plus is a modified version of BOSS 200, really kind of combines some of that CAT chemistry. Really, we're using this primarily on sites that have really high concentrations, definitely NAPL, and we've been, over the last few years, transitioning some of our BOSS 200 sites to 200 plus ever since the CAT 100 technology was developed. So that's really it from a technology standpoint. Now we'll kind of really focus on the applications now. And so first thing we have to really discuss is the difference between liquid injections and slurry injections. So when I refer to liquid injections, we're talking about primarily things like chemical oxidants. So say permanganate, persulfate, EVO. So technologies like that are really solutions. They're really liquids. And these are generally applied low pressure, low flow, not always, but often are. And you've got some flexibility with how you can apply those technologies. So you can use injection wells, for example, or you could use a long DPT 5 foot, 1.5 meter screen. But in general, it's difficult to treat sites where your target zones are lower permeability, lower hydraulic conductivity zones. So silts and clays, harder to treat with those technologies, just because you need to apply pressure, especially in something, say, like a clay, to be able to get the material properly distributed. So now compare that with slurries. So activated carbon, so the BOSS technologies, the CAT technologies that we refer to, zero valent iron would fall into this, EZVI. There's a couple other technologies that would kind of fall into this that are solids. They are suspensions. So we need really higher energy, higher flow rates, higher pressures to be able to get these technologies properly placed in the subsurface. So because of that, first off, we can't use injection wells. Injection wells are out. The retractable screens, or those 1.5 meter, 5 foot screens, really also don't work because we're trying to put all that energy really in one plane. So I'll show you some pictures of the injection tips that we're going to be using, and it'll make a little bit of sense once we talk about this GeoTAP pre-drill process too, because it's really important that these techniques that we're going to talk about today really are only applicable for slurry technologies. All right. So here's just an overview of comprehensive overview of how we get slurries into the ground. So there's your traditional direct push. So we inject in a top-down manner. We feel like that's best practice, always pushing down into native material. When we get into the GeoTAP method, we use top down there as well. You'll see typical setup there on the right, where you've got your injection trailer tethered to your direct push unit, and it's going to look very similar for this GeoTAP setup as well. But there's an intermediate step that we're gonna talk about here in a minute, where we're using like sonic or augers, for example, before we use direct push. Bedrock, so that's done with straddle packers. And so where we isolate, once we understand the architecture of the fracture network, we can isolate the fractures and be able to inject these slurries. We have systems and the packers to be able to do that. We have separate webinars that are just focused on that. So again, if you're interested, check those out, or drop me a note. I can make sure to point you in the right direction. And then lastly, soil mixing. We do quite a bit of soil mixing applications if you have the access. If you're doing an excavation, it's really the best way to get any technology properly distributed is with physical mixing. But we obviously don't have that option on a lot of our sites, which is why we have to default to injection techniques. So just a few pictures here. So this is actually this is our deepest pre-drill site. Went down to about 170 feet, I believe. And this was in South Carolina. And so we're using the GeoProbe Sonic to get down to that depth. As we'll get into here in a minute, we backfill that with bentonite and then re-drill that with direct push. Here's just a shot of the packers. The packers that AST uses are there on the left, about a 1.5 foot difference, about 18-inch interval between those packers. So we can really isolate individual fractures in the rock network. And then it's just a shot of just trenching in this material, which is, again, if we have ability to trench or soil mix in, really not the focus of this presentation, because if you're here, you may have sites that where you've got direct push refusal, so trenching or soil mixing may not be applicable. All right, so GeoTAP simply combines traditional drilling, so augers, so solid stem augers, for example, sonic techniques with direct push, and also a really key piece of the process is these slurry injection systems that AST has developed over the last 15 years to be able to inject at the proper flow rates and pressures. So where do we use this? I'll show you a map of the US here in a minute, where we've used the states where we've used this technique, and they really vary quite a bit from, say, gravels, cobbles, glacial till, weathered bedrock, fill, caliche. There's a whole list of sites where, these are the sites that are in the middle of, it can't direct push it by itself, and it's not competent enough to hold a packer. And to be honest, there are quite a few sites where we don't know when we go into it, which of those, is it going to be a site where we have to use packers? Is it going to be a pre-drill site? And that's going to involve some level of pilot testing, because we've gone out to a number of sites where, just looking at the boring logs and speaking to our clients, that we go in assuming that it's going to be fractured rock, and go in to put an open rock borehole, and it starts to collapse to the point where we can't use packers. And so it ultimately gets transitioned to a pre-drill or GeoTAP site. So again, you're gonna pre-drill each location down to whatever your target injection depth is. We're going to backfill that hole with bentonite, and we're going to hydrate it, build it in relatively short lifts. We want to make sure that we don't get bridging of the bentonite down hole, and we let that set up for 24 to 48 hours minimum, and then we can come back and probe through that bentonite with the direct push unit. So a couple caveats here. So number one, again, I mentioned, you want to make sure that the bentonite sets up. Two is, there's going to be, I would say, a shallow, you probably don't want to, in general, you're not going to use this technique shallower than, say, 10 feet, 3 meters. Okay. In general, excuse me. Sorry about that. So we're going to, again, so those are really, there is no depth limitation. If you're talking about, if you're working at really deep, relatively deep depths, so that site that I mentioned in South Carolina, we went down to 170 feet. You're going to run into some, you're going to make sure that you have the right injection system out there to make sure you're not limited from a pressure standpoint. But in general, let's say you're working from 10 to 50 feet below grade, you can use one of our normal BOSS injection systems. And so that high energy injection cuts through the bentonite and gets out into the native material. Okay. So we're talking about this high energy emplacement. And so here are some shots that were taken at our office, our headquarters in Kentucky. So this is using, we have a couple different systems that have different flow and pressure profiles. This system that was used here that you see was the system that we use primarily for bedrock applications or for deep overburden applications. And so it's capable of going up to 300 gallons a minute at like 2,500 PSI. So overkill, obviously, if you're doing a relatively shallow application, but if we're injecting in fractured bedrock, or again, if we're in a weathered, say, silt claystone that's at 50 feet, we may end up bringing out this larger injection system. So what they did is they ran different flow rates through these injection tips. And so you can see there on the right-hand side, a couple examples of injection tips that we use. So all of the injection, all of the ports are in one plane. And so you can see here, these are at going from 20 from left to right at the top, 20, 60 gallons a minute, and then 120 and 250 gallons a minute down there at the bottom. So it's very rare that we're injecting, I'd say, over 100 gallons a minute, especially for these applications, but that does occur from time to time. So here's that map that I had promised you of our pre-drill applications. The only thing that's not noted on here, we've recently used this technique in Australia. So that would be to get them added onto this slide, but we've used it pretty much coast to coast in the US and in Canada, and now in Australia as well. So the designs are going to be a little different, depending on, again, it's here's just your spacing. You know, there's a kind of a standard layout of an injection grid. The injection point spacing probably between 7.5 and 10 feet. It's going to depend on geology, depth below grade. There's going to be some variables there, but so that's a typical range whenever we're doing, say, source area injections. And then if we're doing a PRB using this technique, generally, again, that's 7.5 to 10 foot spacing with 3 to 5 rows of points. And those designs are going to be driven primarily by the mass flux that's coming through that cross section. Okay, so that was just a brief summary of the technique, and so we try and keep these to about 30-35 minutes or so. We understand that time is precious, especially at the end of the calendar year here. So I'm going to run through 3 or 4 quick project summaries, and then we'll open it up for questions. So this is one of our oldest sites, or continually monitored sites. This is a pre-drill site up in the northeast US, and the pilot test was in summer of 2015, and then full scale was done in later that year, the first phase, and then the second phase came in about almost 2 years later. And so the reason why we needed to use pre-drill out on the site is that we had about 20 feet of construction debris. And so sonic was used at each of these locations that you see here, down to competent bedrock. MW204 that you see here. So this is the up gradient well that's going to be closest to the source. This was our original pilot test well, and this got ultimately consumed by the full scale design, the full scale layout, excuse me. And so the down gradient monitoring point was moved here to MW207. So whenever I show you the data here in a second, so this was our pilot test data, then I stitched together the MW207 data after the full scale was implemented. So it's about 150 feet long, and total of 88 injection points on that 7.5 foot spacing that I had mentioned earlier. And the interval varied quite a bit depending on where competent bedrock was, and that varied between 34 and 57 feet BGS. And down below, you'll see that our pressure range was 50 to 400 PSI. Now that subtracts out your system pressure. So that has been taken out already. The injection flow rate was 55 gallons a minute, and we were injecting 40 gallons of slurry per interval. And so that's injecting every 24 inches vertically. And then we offset that distance. So easy way to think of it is all the even injection points got even depths, and then all the odd injection numbers got got the odd depth. So they are offset 1 foot vertically between the adjacent points. Here's what the site looked like after all the injection points were pre-drilled. And we came in with a geoprobe and pushed and then injected over that bentonited interval from the groundwater down to that competent bedrock. And so here's the total BTEX. They're on the primary axis, that's in ppb. That's in blue is what's on the up gradient well, and orange is again everything on this side of this solid line. This is MW205. This is MW207. Excuse me, MW205, MW207 here. And so you can see that the influent BTEX concentration did vary quite a bit, call it an average of about 1,000 parts per billion. And we've had really low detections, essentially just detection limits coming out the down gradient side. And you can see there, it's been for the data that I have, we're at about 1,900 days post pilot test. Second site, so this is another northeast site. So this is in Brooklyn, so New York City, and it's a former retail gas site. And so we applied using this GeoTAP technique after ISCO was attempted multiple times, and direct push just couldn't consistently penetrate this gravel layer that extended down to about 40 feet. And so a sonic unit was brought out to bypass that refusal zone. The bentonite was backfilled, and then we came back with direct push, just like on the other side. Here's this data. See a lot of variability, so I'll kind of walk you through it here. There were 5 rounds of sodium persulfate that were injected on the site, and I'm calling that day 0. I didn't have a lot of data as to when those were done, so I'm just calling that day 0. There was also Regenox applied, say day 1200 or so in this timeline. And so we see between all those chemical oxidation events, we just see a lot of variability. And really, I think we just couldn't get access to where the mass was. At this particular site, there was a lot of mass underneath the road adjacent to the site. I just don't think they were able to get enough material out there to get it properly distributed. So I had a lot of variability. This vertical line here is when the Boss 200 was injected, and the no further action was issued here about 3,200 days in the process. It's about 10 years of data that you see here. And so I think, as on most of our sites, and this one falls into that, obviously it comes down to distribution. I think when you have these challenging geologies, using wells, so for example, on this site where you've got injection wells, or you've got they couldn't get direct push past the gravel, so they're using a combination of direct push and wells to be able to deliver the oxidants, and it just could not get it properly distributed. So so now we'll talk, those were 2 hydrocarbon sites. We'll talk about a couple chlorinated sites here. So here's a site that's in New Jersey. And so it was, you can see a description of the geology there. Had partially weathered rock from 3 to 22 feet, and then competent bedrock below that. And depth of water was about 10 feet BGS. And the contaminants of concern were TCE and 1,1 DCE. And you can see there at the last bullet that solvent impacts weren't above the limits for the overburdened soils. And so we were really focusing on treating the groundwater in that partially weathered rock and bedrock. So the TCE was over the 1 microgram per liter New Jersey standard. The overburden impacts really were non-existent. That soil bedrock interface was very shallow, approximately 3 feet BGS. And it was suspected going in that partially weathered rock transition zone was really holding up that mass. And it had about 87 to about 100 micrograms per liter of TCE in groundwater. So the total treatment area for this site was about 3,500 square feet. And treatment interval was, and it was broken up between a couple different methods, was the overall treatment interval was 10 to 55 feet BGS. And with the shallower transition zone, using that GeoTAP method that we're focusing on in this presentation, and that was from 10 to 25 feet. And then below that, we used those straddle packers that I showed you before in the competent rock to be able to isolate the fractures and inject BOSS 100. So on the front end, and it's recommended for really most sites and really all bedrock sites, is to go out and do some additional characterization if that data is not available. So downhole geophysics and sampling of, in this case, the partially weathered rock, as well as the fractures down in the competent bedrock. So 3 open rock boreholes were advanced to about 85 feet BGS, and 10 GeoTAP points were installed to 25 feet. Downhole geophysics were performed, as well as some downhole straddle packer testing. And so that's primarily there. We're just using water to isolate the fractures that are identified by the geophysics, and using a set of transducers to be able to see what the overall distribution and the fracture network looks like by monitoring the adjacent monitoring wells. And we're able to show that it was very low impacts, relatively speaking, that were in the borehole fractures. So that brought us back to our initial thesis that the partially weathered rock was the source for all of those dissolved impacts. Okay, so BOSS 100. So this is the chlorinated solvent technology that's activated carbon that's impregnated with reactive iron, was deployed at this site. And so it was injected in the fractured bedrock, that using shuttle packers, and then it was injected in the partially weathered rock using GeoTAP method. Okay. And the transition zone injections we used, because we were out there using our bedrock injection unit, which is the one that I showed you those injection tips with the fluid coming out at the different flow rates. That's a system that we use there. We use that same system here. And that's generally what we use in fractured bedrock. And that was already on site. So we use that for the partially weathered rock as well. And we used flow rates of between 70 and 100 gallons a minute for both the partially weathered rock and for the fractured bedrock. All right, so our max baseline concentrations in MW2, which was one of our target wells, that was 73 micrograms per liter for TCE and just over 3 micrograms per liter for 1,1. And that was prior to the transition and the bedrock zone injections. And after the injection, you can see the data there. All 4 monitoring wells within the treatment footprint achieved the project objectives of 1 part per billion for both TCE and 1,1 DCE in less than 6 months after the injections were performed. Okay, so we'll wrap up here with just one more site. So this is a site that I was involved in. It's a former Atlas missile silo site that's in Nebraska. So it's I guess one of the 4 that are not in the Northeast U.S. So it really had an unidentified source out on the site. We had one well that had really elevated concentration, suspected DNAPL. Perch groundwater table was at about 50 feet BGS, and our target interval was 50 to 60 feet below grade. And it was a low plasticity clay till, just could not get consistent. I don't think we could get any deeper than 20 or 30 feet with direct push by itself. And so this was quickly transitioned over to a pre-drill GeoTAP delivery method. Okay. And so out on this site, we were tasked with performing a pilot test to see if we could get the BOSS 100 distributed properly. So as part of our remedial design characterization, we went out and installed 4 monitoring wells, 1 multi-channel well that had 7 channels between 22 and 70 feet BGS. And we sampled soil every 2 feet or so. So we send about 115 total samples to the RPI Project Support Lab. That's in Denver. I mentioned that early on. It's a pro bono laboratory that RPI runs to help support our projects. So they run pre and post analytical for soil and groundwater to help support our projects. So as I mentioned, this is why this site is really in this presentation. We had shallow direct push refusal. So we used 4 1/4 inch solid stem augers to advance a couple different depths. So again, this was driven by the data that was collected during that RDC process. We had 14 points. Those are the red points you see there. Those are to 70 feet BGS. And the blue points there, those were 7 points. Those were advanced only to 54 feet BGS. Since this was a pilot test, we did vary the spacing a little bit from between 5 and 10 feet for a total of 21 injection points. So we used 2 1/4 inch rods. And as I mentioned earlier, with traditional direct push or with pre-drill GeoTAP, we prefer to go top down. And the flow rates you can see there, we had a range between 35 and 62 gallons a minute. When we go out to pilot test the site, we do try and vary that a little bit to be able to see, trying to find that optimal flow rate for that particular site. And we can also, we really haven't gotten into this on too much. In this presentation, it is included in others. We can vary that injection tip geometry as well. So we can alter, use different tips that have different number or different area of injection ports. So if for example, if your injection flow rate is static and you lower the overall surface area of your injection ports, then you're going to increase the velocity of the slurry coming out of those injection ports. On this site, we had an exit velocity of over 4,000 feet per minute. And you see there we had about 7,600 pounds of BOSS 100 installed. And here's the data from this site. So there's a huge gap. The funding for this project was really for the pilot test, and that was really only a 6-month monitoring period after the injection. And then the site sat for a while, and you could see it was collected late 2019, early 2020. But we're able to see for our target well, we had an overall 99.4% reduction. That was 1,300 days from our RDC baseline. And the NW 2728, these are a couple wells that are side gradient from our injection area. And so we had a 46 to 90% reduction. And again, these wells were not within the treatment footprint. These were outside side gradient of where we did the applications. So thank you very much for your time. I'm I think about 34 minutes in, so we're right on schedule. So we'll go ahead and open it up for questions. You can use the Q&A tab up at the on your sidebar and send those over. And let me go. I see we had a couple questions submitted during the presentation. Okay, so first question is, are there alternatives to BOSS 200 that can be applied at low pressure liquid injections? Can the slides be provided? Those are not technologies that we provide. And so they're not covered in this presentation. So, but that really doesn't fit with this presentation because you can't inject liquids, or you can't inject anything low pressure using this technique. Because what's going to happen, as you'd imagine, is that if you try and low pressure, low flow, so if you go in and try and pre-drill a point, so you advance it using whatever method you want, backfill with bentonite, and then you put a 5-foot screen down there and you try and low pressure, low flow it, you're not going to get through that bentonite. And what's going to happen is you're going to end up pushing your bentonite out to the surface, which is the path of least resistance. So again, I don't recommend attempting this technique with liquids. It's really for slurries. And the next question here, what are the typical upper ranges of injection pressures in low K or bedrock zones? Excellent question. I would say the upper ranges, again, you have to look at, there's really two different pressures, right? Whenever you're looking at injections. So you've got your system pressure. So you have your gauge pressure, what's showing up on your injection system. So that's the sum of your system pressure and your downhole pressure, your injection pressure. There's quite a lot of pressure loss in these systems. So you have to subtract that out. So on the one slide, I did mention that 50 to 300 psi. I think it was the site that was in the Northeast, the one that was the truck stop, and that had already taken out the pressure. So if you take that pressure out, so now we're talking about just downhole pressure, I would say in general you're looking at a couple hundred to maybe 500 psi, but it's going to be a function of how deep you are, right? So if you're talking about a clay application that's, let's just say for the purposes of this presentation, we're talking about, say it's like a clay stone that's at 20 feet below grade. I would expect a couple hundred PSI would be needed as your fracture pressure. You know, your maintenance pressure is going to be something lower than that, 50% maybe of what that fracture pressure is. The deeper you go, the higher that pressure is going to get, which is why I mentioned there is a depth limitation with some of these injection systems, and you need to make sure that the system that you bring out to your site to really, I mean, for any injection, but for this technique here, is appropriate for the depth. So that site in South Carolina that I mentioned, we went down to 170 feet. We used that bedrock unit that had that higher pressure capabilities. Lastly, is there a bentonite setup time which you do not want to exceed before injection? I mean, I think that's going to be a function of depth, but I would say within a month or two, I would say. Now it's going to be somewhat depth dependent, and because if it's a really deep application, then you may have some refusal issues trying to get back down. And so we evaluate those on a site-by-site basis. Maybe we make modifications to the bentonite to just be able to make sure that we can get back down to that total depth. But I know that some of these pre-drill sites, especially on the shallower side, say called shallower than 50 feet, you know, we can actually go out and re-inject on these sites. We can get back down to that bentonite quite a long period of time. But I would say probably within, a month or two, you'd want to be able to get out there and do the injection work. But on the minimum side, usually 24, 48 hours is all you need. Well, those are the questions that were submitted. I'll wait a wait another minute here to see if any other questions come through, and I can just start my wrap up. Thank you all very much. I know that there are many of you have attended multiple presentations over the course of the year, and so really appreciate your time. We know that it's valuable, and so if there are no other questions, thank you, everyone. Enjoy the holiday season and Happy New Year. Thank you.